because now we're going to recast the principal components. So I want to think about this in a slightly different way. So if you look at what are we doing with principal components, we've got these principal axes, the axes we're going to project the data onto. The projections onto those things are going to be the coordinates of the principal components. And we could do that in two ways. We can get the eigen decomposition of x transpose x, or we can go with a singular value. In either case, y is going to be taking every row of x, projecting it onto every column of v, or just taking the product of u and d sigma from the singular value decomposition. Okay? So we don't really need to know the principal axes at this point. They may be helping in interpreting the variates at the end, because you know that each new column of y is going to be some linear combination of the original x's. And so the v's are kind of giving you the weighting of those. But to actually get the coordinates, we don't need the v. Okay? So the thing is, we could also take y transpose. If we take y transpose, just substituting for y and its transpose, we're going to end up with u d sigma squared u transpose. And that's the same as x transpose. Right? So if I had x here and its transpose, I'm going to have an u d sigma v transpose v d sigma u transpose. V transpose v is going to be the identity. I'm going to end up with this as XX transpose. So y transpose and XX transpose are identical. Which means if I started with an eigen decomposition of XX transpose or y transpose, I could get d sigma in u from that. So I've got a choice. I can work with x transpose x, or XX transpose. Okay? Everybody see that? So the thing to note is that these things have different dimensions. If x is n by p, right, then x transpose x is p by p, and x transpose is n by n. So depending on the relative size of p and n, one of those matrices may be much larger than the other. Right? Okay, so let's look at XX transpose. XX transpose, remember we can look at this just like we looked at X transpose X or X itself. It's got some interesting structure. X has got the coordinates in each row, so we've got n points, and there's X transpose now appearing as columns. So if I do the matrix multiplication to get the ijth element here, I'm going to take the ith row of this matrix times the jth row of that column. That's going to be xi transpose xj. Okay? Which is just the inner product of xi and xj. Right? Everybody's okay? This matrix has a name because it appears so frequently in many problems. It's called the Gram matrix. So XX transpose has a particular name, this matrix of inner products. It's called the Gram matrix. And remember, our x's in this case were all centered. Right? That is, we subtracted off the average from all of the x's, which means if I were to add up all the rows here, if I added up everything in this first column, it's going to be x1 transpose times x1, x2 transpose times x1. They all have this x1 in common, so I can factor it. So it's going to be x1 on the right-hand side times the sum of x1 plus x2 plus xn, all transpose. And that sum equals 0. Okay? Because we centered the x's. Yep. And the sum of the rows. because we ensured that all the xi sum to 0 because we subtracted off the x bar from everything. Okay? So every row and every column sums to 0. So you might want to just write this down, that XX transpose is this matrix of inner products. And well, the principal axes, the V's, they're just that, they're axes, right? So they just correspond to the directions. And we want to remove those directions that have smallest sum of squared projections onto that direction, right, of the data. And for that to work, they have to be near one of these linear subspaces or a linear manifold, okay? For all those projections to be close to squared 0. They're going to be near a linear thing. Okay, so what about this? Do they lie near any linear manifold, those points? Well, no. Any direction I look at, the sum of the squared projections is going to be the same, roughly the same, depending on how they're distributed around that circle. But it sure is clear that they aren't occupying that whole two-dimensional plane. They're living in a smaller region, right? So I want to think of that region as this is really, it's another manifold that they're lying on a smaller geometric structure, right? But it's not linear. So how might we capture that? Well, we could think hard about what sort of nonlinear structures might we look for and figure out, well, how do you actually find nonlinear things? Or we could say, can we turn this into a linear problem? Okay. So how might we turn that into a linear problem? Well, one possibility is to just go back to this picture, is to think about polar coordinates, right? If you transform this to polar coordinates, everybody's at the same radius. All they're doing is differing in angle. Transforming to polar coordinates, that means on the r, the radius side, you've just got one number. And on the theta side, the angle, you've got this range. Okay? So that's thinking about taking this vector and transforming it to another pair of vectors, pair of coordinates of another vector, which we'll call features, just to make it, give that F meaning. So different pair of features using this nonlinear transformation. Whoops. To the radius and the angle. Okay? So another way of going this at this problem is, rather than thinking about how to transform this, is can we think about, is there some way of getting on this nonlinear manifold and following the points around? Can we somehow get on the manifold and move around that manifold? And what do we mean by that? Well, I kind of mean that these points are close to each other if they're close to each other along this circle. It's almost as if we're looking at the Earth and looking at great circles here, right? We want points that are closer, the ones that are following the great circle. So some way of saying that is we're looking for a nonlinear manifold where the points on which the points lie, or with real data that they lie near to a nonlinear manifold. And the objective there is going to be trying to preserve the local structure. Okay? So in this case, when we got things along here, it's pretty clear that that polar coordinate transformation is going to work fairly well. So let's do that. So I'm just going to, I'm going to go and do that polar coordinate transformation and get a new data frame. Then I'm going to do the singular value decomposition of that new data frame. And you'll see that it has two singular values, one here and another that's effectively 0. So in this new space, there really is only one dimension. Okay, and there it is. And you knew that was going to happen. You've got the same R, it's just the angle's changing. So this trick here is, can we move to a different coordinate system and use the linear method? Is there another coordinate system in which the thing is linear? Okay. So there we kind of knew the answer. So it's a nonlinear transformation, but we're in a coordinate system where all the data lie in a one-dimensional subspace. Alternatively, we might just add features. So this is really counterintuitive. I've got a two-dimensional space, and I'm going to go from the two-dimensional space to a higher dimensional space, which is pretty weird if you're thinking dimension reduction is the goal. So when I go to that higher dimensional space, and I plot the data in that higher dimensional space, you see the pairs plot here, you can certainly see for a couple of the features, they are really near a linear subspace, right? That is, anything orthogonal to this pair of features is going to have no variation. It's probably not perfectly orthogonal, but okay. So kind of counterintuitive. If I up the dimensionality, there may be linear structure that I can pick off. So if I was picking that off, I'd say there's, looking at the singular values here, I've got 3 singular values, 9, 8.5, and 6, and I've got 1, 0. So I've gone from a two-dimensional space to a four-dimensional space and saying there's really only 3 dimensions there in that four-dimensional space. But I can find that with using the linear method. Okay. And this is where V comes into some value. So here's the last eigenvector, or the last right singular vector. And you can see what it's the values. So it's telling me that this last guy here is occurring on the last one where it's 0 happening, is that it looks like 0, 0, and these are about the same, and they're about 1 over root 2. Okay? So this line here is orthogonal to 1, 1, the 1, 1. Everybody see what I'm doing? So it's weird in a couple of ways. One is that I'm saying, let's take this smaller, I want to reduce dimensionality. Let's take the smaller dimensional space, move it up to a higher dimensional space, but use some linear methods there that maybe allow me to reduce the dimensionality again. Okay? Although in this case, I'm down to 3 instead of 2. I seem to have done things, it looks worse. Okay? So, any questions? It's just going to get a little more abstract. Okay, so for a simple data set like that, it's kind of obvious that it's on a lower dimensional manifold. Just it's nonlinear. And it's obvious that I can find, if I go up, I can find some directions where there's very little variation. So, what are we doing here? Well, let's imagine that I've got a vector that's we start with that's in p dimensions, and I consider mapping that into some other dimensional space, M, right? And M could be larger than P. So I move it up into a higher dimensional space by some mapping psi. And psi can be as nonlinear as you like. I'm not defining it, it's just moving it up into a higher dimensional space. So Fi for the of x, applying psi to xi is going to give me a point in that higher dimensional space. And that's going to be the features in that higher dimensional space. And so you'll sometimes see writers saying, I want to talk about the feature vectors and I want to talk about the feature space. And that's supposed to be M. I don't know what happened there. So that's R to the M. So this feature space, the data lie in some feature space, maybe lower dimensional manifold. That's a subspace of where you map this to. Now what's cool is it doesn't matter how big or small M is, you still have the same number of points. Okay, so N stays the same. And that means if we did principal component or eigen decomposition of the Gram matrix, it's always going to be N by N. So X transpose, as it were, it's always going to be N by N, whereas X transpose X may be, it would be capital F transpose is going to be N by N, and F transpose F would be M by M. So that means I could actually map this into a much higher dimensional space. In fact, I could map it into an infinite dimensional space. There's nothing stopping me here, because when it comes to doing anything related to dimension reduction via principal components at least, I'm going to be looking at an n by n matrix. I'm never going to have an infinite by infinite matrix. I'm going to stick with the one that has this low dimension of n. So don't worry about how I get to an infinite dimensional space. Pick any large number, 5 billion, we could go up to that dimensional space. And if we only had 1,000 observations, we're still dealing with a 1,000 by 1,000 matrix. Okay? Everybody get that? Make sense so far? Lots of raised eyebrows. Where are you going with this? Well, so as I said, if we look at this vector, we map all the x's into all these f's, right? So this f now, the capital F is going to be an n by m matrix, right? Where m could be very, very large, much larger than p, much larger than n, could be infinite. But f transpose is always n by n, even when m is infinite. All we need to do is get the elements of this Gram matrix, which I'm calling K here since I've changed spaces. That's going to be the inner product of these feature vectors. That's going to be the inner product of that mapping of the x's up to that higher dimensional space. So that's some inner product on that higher dimensional space. And we'll give that a name. Capital K of xi, xj. So the funny thing to do this is, I don't even need to know psi. I don't need to know what that function is, as long as I know what the inner products are. So what are the inner products in that feature space? Right? That is, if you tell me what that thing is, what the inner products are in that space, I don't even have to, not only do I not have to actually apply psi to the data, I don't even have to know what psi looks like, as long as I know what the inner products look like. Okay. You guys got questions? You bet? Okay. So this is a trick. It's sometimes called the kernel trick. And this is called a kernel function, not to be confused with how we've used the word kernel before. And the idea is that all I need is the inner products in some higher dimensional space. If you tell me what that is, I can go and treat this as if it were that Graham matrix and do dimensional reduction using PCA. Okay. In fact, a lot of methods work here using this kernel, provided that any method that only depends on the inner products will work, right? If all you have are inner products, if you've got methods that depend only on inner products, you can apply it to this feature space. And it happens that principal components is one of those things that only depends on inner products. So here's some common choices, some suggestions. So this is a polynomial kernel. And you've got a couple of parameters here, a location to scale parameter and a dimension. And so you, sorry, let's not call that a dimension, a power. And you take the inner product, usual real space inner product here, and you scale it, relocate it, and then power the thing up. And we'll call that the kernel. So that's going to be the inner product between x and y in this higher dimensional space. And you can easily imagine how that works. So for example, if we had three-dimensional data and just pick scaling a 1 and no offset, the kernel looks like this. We take the square of that inner product, and when you expand that, you're going to get like that. And you can actually see that it's the inner product of these two vectors. That's a vector only involving the x's. That involves the y's. The same function applied to each. So we can actually read off what the psi function is. Okay? There's another one called a Gaussian kernel, or sometimes a radial basis kernel, mainly because it looks like a multivariate normal. So it's an exponential to the squared length of the difference between the two vectors divided by 2 sigma squared. And that also is an inner product, but we've mapped it now to an infinite dimensional space. And you can do the same thing we just did with the polynomial of degree 3 there, if you'd like. If you think about doing a Taylor series expansion of e to the x on that product, you can actually make this look like the x's and the y's separate, and it looks like an inner product. It's just an infinite dimensional sum. Okay, so we've actually mapped to an infinite dimensional space by looking at that thing. It's a lot of faces like your brain hurts or something. Is that okay? All right. So the hyperbolic tangent or sigmoid is also another kernel. And there's a theory that goes and nails this down, saying that these are, in fact, inner products, courtesy of something called Mercer's theorem, that gives the conditions on the function, the kernel function, so that it can be expressed as an inner product. Okay. So, as in almost everything that's in this course, there's less here than meets the eye. So the idea is that all we needed to work with were inner products. If you give me the inner products, I can get PCA. I can get principal component analysis. Right? If you tell me the inner products. Some inner products effectively are like mapping the data up to a higher dimensional space. But hopefully in that higher dimensional space, we'll be able to pick out interesting linear structure. Okay. So, last tidy up thing here is that we want these guys to be centered about 0. These feature vectors, same as the x vectors. And so a simple way to do that when you've got that kernel is just to make sure that you center the rows and columns. And you should recognize this by now. This piece here, if I can grab it, it's not going to let me grab it. This in between the parentheses here, that's I minus P. That's just a projection, right? And it's this part here is projecting onto the 1 vector. So this is everything orthogonal to the 1 vector. This is how you actually center the rows, center the columns. Subtract off the row means and the column means and add the overall mean back in is what effectively happens here. So when I apply this, projecting all these vectors onto the part that's orthogonal to the 1 vector and all the row vectors orthogonal to the 1 vector, I end up with saying just take the original thing, subtract off the row means, subtract off the column means, and add back in the grand mean over the whole thing. You can just show that for yourself. Okay? All right, so let's look at this. So in our R, there's a package called Kernel, which allows us to do Kernel PCA, Kernel Principal Component Analysis, and it's this kpca function. And you can pick a variety of kernels, right? So the radial basis function kernel, or the Gaussian kernel, the polynomial kernel, the sigmoid or hyperbolic tangent kernel. So let's do one of those. Well, let's put these guys down for a bit. And where's my R? There it is. This should work, he said. So I'm going to get the results there, pick off the eigen values. Tick, 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 tick. Right. D1. Take the first 20 of these guys, do the scagnostics on them, nav graph, all the usual things. Apply the glyphs. All right, so now we've got this in on this data. So we've got the scagnostics here. And wow. So let's look at the clumpy guys. V13 seems to be the thing here. And I guess we're going to have to play with this next day. No, we've got a few minutes. World. And so you can see that really clumpy behavior there. In this higher dimensional space, we're seeing some separations in there, Jeff. I'm not faring very well today. So we'll play with this a little more next day. And if I look at non-convex, but not skinny, you see I'm actually picking up all kinds of the 3rd, the 11th, the 20th, 18th. And boy, so there's all these straight lines in there that are showing up. And so you might ask, why are these guys all going off in that direction? Right? And so there's things that are happening, you know, which way the face is looking, what is he doing with his mouth. These guys are exchanging positions in this. And again, we'll play with this a little at the beginning of next day, looking for sparse. So, the usual exploration. Is there more information in the principal component analysis? And that's called Kernel PCA. And all that's happening is, again, we're mapping up to a higher dimensional space and then doing principal component analysis. And the trick is you don't actually have to do the mapping, as long as you know the inner products. Okay? And you'll see this in other things, in, you know, in machine learning courses. This is the kernel trick. And any linear method that's ever been done in statistics, you apply this kernel trick to it, and you've got a machine learning algorithm.